Hello everyone, I'm Tejas from and we're gonna see my project on brain tumor detection. So what this project is basically it detects whether a person has brain tumor or not based on the MRI scan taken of their brain. Let's see how this works basically. So this is the site where the project is hosted, and you can see we can just select a picture here, and we have several data sets. And let's say I'm selecting a picture of a brain with pituitary tumor, and then I give open and we get the result as pituitary tumor. Now let's see how this code works and how the implementation is done. And we'll start with the main model definition. So for defining the model, we are using Keras and sklearn. These are like important modules of machine learning. And we also use CV2 for what is it, image handling and like manipulating images basically because we need to pre-process because the data sets are in images, so we need to pre-process it. So first we start by creating an empty list of image data. This is done because there are like thousands of images and we need all of the data of all those images as our training set. And then we create image labels so that we can basically like label them, kind like we just what do we say, we just give them a label like what kind of tumor it is and like name the images. And then what we're doing is that in our data set, you can see the data set is linked the data set is taken from Kaggle, which is linked in the GitHub README page. You can just verify it quickly and download it if you want to. It's a very good data set with over like with thousands of images per data. And then what we do is that you can see that we have a training and testing data sets, right? Because that's how machine learning models always work. So in training, you can see we have all these four types of tumors. I mean, three types of tumors and no tumor. And in testing also, we have three types of tumor and no tumor. This is done so that like the model can train with the training data set, and then we can like predict the accuracy of the model using the testing set, or which is also known as the validation set. And then what happens next is that in this we're just linking this training path and testing path, like the folder, and then we're basically appending all the images which are present in that present in the directory into this image data and image labels. And we convert the image data and labels into numpy arrays because they're obviously like faster and like more efficient to work with than just normal Python lists. And then we just shuffle them. This is done because, well, as you can see, we have like let's say three types of tumor and no tumor, right? So when we split the training and testing set, we need to make sure that the separation is basically even. Like we don't want all just the three types of tumors as the training set and then all of the no tumors as our testing set. That way the model would not be able to predict no tumor at all, because it's called overfitting basically. Like the model only has been trained with like a large amount of data with these three and like very minimal amount of data with this. Like we don't want that to happen basically, so we need it to be even and like random. So we're just shuffling the data set completely. And then we create a list called new data. This is done because, well, there's like certain formats in which a model can detect, or like model is conditioned to, and like we're just converting our images, pre-processing. This is known as pre-processing, and we're just pre-processing the image. Like for example, we're changing that into grayscale, and then we're just getting the edge map of the image, and then like the edge map is basically what we give as like the raw data to our model. And then we create again we make the new data into a numpy array, and then we create the training testing again. Like see, above, like we do have the testing and training data set, but that's like a data set that is given by Kaggle in itself. We're just appending both training and testing, and then we're creating our own training and testing data set kinda. So now we just have training testing, and we use train test split, which is like a default module in scikit-learn, and the test size is given as 0.1. What this means is basically that 10% of the data will be used for testing. That is, if there are like nine, or like let's say there are like 1,000 records in total, 100 of them will be used for the validation, while the remaining 900 will be used for training the model. And then we give y, we need like y, and we need to like change it, right? Like we need y values separately, so we are giving y train and y test. And we're just changing the y values, which is like right as of now it'll be like either pituitary tumor, glioma tumor, etc. And we're just changing that to categorical, and we use a default module called to categorical from uh, TensorFlow. And then this is where we define the model. It's comes under Keras sequential, and it's a 23 layer deep learning model. What 23 layer as in, like there are like 23 hidden layers. As you can see, there are like convolutional layers, MaxPooling layers, dropout layers, etc. with activation their own, each have their own activation function basically. And Yeah, that's about it. We just define the model. You can just play around with this like this. The number of layers and what layers we're using totally depends on what project that we're using. And then finally we're just compiling the model, like we're basically like compiling the model, and like we're saying the loss function should be categorical cross entropy, and the optimizer as Adam, and obviously the metrics in like most of the cases the metrics would be accuracy. And then we're fitting the model. Well, we don't have to necessarily assign this history is equal to model dot fit all the time. We're doing that in because, well, initially we need to like measure the accuracy. If we need to like measure the accuracy of a model and like have, like we if we need like other things to do with the model, then we basically assign it to a variable, or we can just give a model dot fit of x train, y train, and epochs. And the epochs are given as 30, and again we split the validation into 0 point validation split as 0.1. And then here what we do is, this is like a crucial part. So as you can see, the when we run this program, it takes like a really long time to run all these epochs, because a model is like trained from the start. And like if we need to predict, if we could just we could, in a way, we could give model dot predict of some value, right? Some value, but that's not going to be optimal in the way where like the user is simply using our software, because then the model would again train from the beginning to that data set, and then again like run all the 30 epochs. That would not be optimal at all. So what we're doing is that we're saving the trained model as h5, and h5 file, like model.h5. If you like if you're using this thing, you need to like run this run this model definition.py once, and you'll have this model.h5 file in your root directory, or whatever directory this code currently is present in. As you can see, I've already run this code, so I'm not going to run it again, but after running this, we get the model.h5, and we're going to use this in our other application code, where we basically just import this model which is trained here into our application. Now let's see how the application works. It's basically it's like a very simple web app that's done using the Django framework from Python. So let's see what happens here. Like as it's just a default template taken from Django, and like there is a home page. The home page, you can see like here the home page, and as you can see, there is like an empty form here where we can just input our images. So that's basically what we're doing. And we all know, when we input an image into the form, the method becomes post. So we're saying if the request dot method equals post, that is like, if we're basically saying that if someone actually just submits anything to the form, let it be anything, whatever they want to submit, if they're submitting it, we fetch that file, whatever they're submitting, we assign that into our file, and then we're basically calculating the result. Result is equal to predict of file. So we're calling a function called predict, and we're giving file as the input to that function. So let's say what the predict function does. This is basically like the main logic of our model. I mean, not our model. This is like the logic for prediction, basically. That like this predict dot file. See, you can see the model here. We load the model.h5 app slash. It's because the model is currently present in the app directory. So app slash model.h5, and we're just loading this model, and then we're loading the image. The image is basically going to be whatever file they upload. Like for example, if I uploaded, say here I go, and then I upload this image 13, then the file would be the image 13. But we don't just need it as a file. We need to like make it in a. We need to like again pre-process this file into like the same way the model was trained on, right? So we're basically just using our pillows. Image library from Pillow, and we're just opening the file as bytes.io, and these are all the same pre-processing that was done during the training, like grayscale, converting them into grayscale, and then we're resizing it, and then we're creating an numpy array, and like we're getting the edge map and all that. And then finally we're giving result equal to model dot predict. This is just normal code, like any like we loaded the model here, and we're just asking the model to predict the result to our inputted image. As you can see, the result would usually, let's say if I just gave an input here right now, after we get the result, you can see that just the result alone would be as a list. What this list is basically like, it just provides a number of like which value is more likely to occur. So this is like currently the highest value here, like 9.99 into 10 power 99 or something, and like that means that this value is like that much likelier to occur than the other ones. So we need to like, we cannot just output this as our result to our users. That won't be really user friendly. So what we're doing is that we're calling a function called argmax. What this does is basically it sees through the list, and like it it sees to the list and like it checks out what value exactly is the maximum, like what index contains the highest value, and then it just returns that. So we're giving predicted class equal to np.argmax of result, and we have the labels here. This is the same labels that we used earlier, so glioma, meningioma, and pituitary, etc. And what we're doing is that we're returning labels of predicted class. What this does is predicted class would give us which index of this result is the highest, right? So as of now we get predicted class as 3. So when we use the pick the fetch the third index of this labels, we get pituitary tumor, which is what is displayed here. And we just so after getting this, so we return this, right? So when we give result equal to predict of file, we get this one, this labels of predicted class. So now we get result equal to pituitary tumor, so we just return a JSON response of this result. So that is rendered in the home page, which is done using JavaScript, HTML, and CSS, and that's basically how the model works. You can try inputting different types of tumor like glioma tumors, and it'll give the outcome basically. And that's about it. Thanks.